The most used tool for discovering new music, it's right in your pocket, your phone. There's a reason why our clients, music producers and artists are concerned with how music impacts a listener on one. Because social media is where everybody's eyes and ears are at. TikTok alone has 1 billion monthly active users. And in a 2020 survey, 75% of all users said it's where they discover new music. There's one problem. I pulled apart an iPhone speaker and the alloy diaphragm is only 10 millimeters, compared to, let's say, an 8-inch woofer on your studio monitors. This comes with incredibly difficult physical limitations and leaves us with the question of how can we deliver the experience of big sounding masters in this little size. Now, I want to let you know, I'm always down for learning, and this video is a journey of discovery on a topic which has pushed my boundaries. And if and where I get any information which conflicts with your own, let me know in the comment section below. I'm always trying to bridge my gaps of knowledge, and I'm open to changing and broadening my understanding of things. First, I found a video on how speakers in smartphones were built and operated. I found some technical documentation hosted by the Department of Physics and Astronomy in Georgia State University. I found a patent filed by Apple in 2016. I pulled apart an iPhone speaker and used some online calculators and previous tests to draw some conclusions. Fundamentally, an iPhone speaker is made of 3 main components: a neodymium magnet, the same found in Odyssey headphones, which provide a stable field of magnetic charge. Seated around that is a copper coil, which measures 0.11 millimeters, and then this coil is attached to a rigid alloy diaphragm, and when current passes through the copper coil, a temporary magnetic field is generated, which interacts with the magnet, causing the coil and diaphragm to move in relation to its magnetic field. Now, mechanically speaking, it's operating in the same fashion majority of speakers do. However, it's doing it on a micro scale. Remember, this diaphragm only measures 10 millimeters. I wanted to understand how this impacted its ability to produce sound. Upon further research, I came across some documentation on the physics of speakers and the interaction on the impedance of air from Georgia State. The specific acoustic impedance of free air is approximately 42 ohms per square centimeter. And we can see by this graph, when wavelengths are longer than the diameter of the speaker, the output drops off rapidly. If I'm calculating across these lines, the diaphragm alone can only physically displace frequencies in air efficiently at 34 kilohertz before it starts dropping off. But 34 kilohertz is outside the human range of hearing. So how is it actually still producing frequencies far below that? Well, the speaker's cabinet plays a big role too. A speaker isn't just a diaphragm on its own, a speaker is a transducer which is made of many components, and this includes the cabinet themselves. So the effective surface area of an iPhone becomes a working component acoustically with the reproduction of sound. And an iPhone measures about 140 millimeters by 70 millimeters, which is 10,000 millimeters square, and roughly the same area of a circle or cone with a diameter of 104 millimeters, which is the equivalent to the length of a waveform of 3.29 kilohertz. Now, this makes good sense because I was able to pull some frequency response tests off the internet of various smartphones, and it's equivalent to where most smartphone speakers' frequency response begin to naturally roll off, because the wavelengths are longer than the area of the transducer and the speaker cabinet, and the impedance drops rapidly, producing low frequencies. However, based on Cohen data provided by the Georgia State Physics page regarding transducers, the rate at which that drops off should be much steeper than the frequency response curves are showing. And at this stage, a lot of it was pretty much over my head. I don't even know if I've got anything wrong up until this point. However, last night, while I was just about to give up on this video, I came across this patent filed by Apple in 2016, Suspension Systems for Microspeakers, and it detailed a missing part of the microspeaker I had never considered: an acoustic port. Now, the maths behind this is beyond my capabilities, so I leaned on some online calculators to see volumetrically how far the lowest frequency of this port could be tuned to, and I was able to come up with 95 hertz. Now, this doesn't mean that's what it's tuned to or any of this is correct. This is just hypotheses and theories. And just because it can be tuned down to 95 hertz doesn't mean that you have a high fidelity full range system with big hitting bass. It still has some limitations, but it's a great missing piece of the puzzle, and I didn't have this before. So physically now, I could confirm where the frequency of efficiency was for an iPhone design and how it managed to reproduce a lower frequencies even though its efficiency tailed off to the lowest tuned port. We've heard it many times before. If you want the low end in your mixes, productions, masters to translate on smartphone speakers, add harmonics. But why harmonics? And that's due to the psychoacoustic phenomena of the phantom frequency or missing fundamental. Now, yes, I had to do some wiki research to gain a better understanding on the language for this, but basically studies show that our brain can interpret repetition patterns in sound waves to psychoacoustically perceive lower fundamental frequencies. As we all know, when you saturate a signal too far with harmonics, things can become edgy, fuzzy, and harsh, and especially if you're saturating the whole signal from 3 kHz and up, your phone is incredible at reproducing those frequencies. So I thought, what if in parallel we introduce a series of filtered harmonics only to the effective range of the frequency bandwidth we know the smartphone speakers are least proficient at, but can still reproduce frequencies to. So basically what I'm saying here is, let's saturate and add harmonics, but only below 3 kHz, because at 3 kHz, it's super clear, it's super edgy, it's going to become harsh. Let's create a parallel chain that filters it and works to the physics of this phone. Let me show you how I've built this. So my aim with all of this was to add harmonics to the low frequencies, but make sure that those frequencies don't go up past 3 kHz, because if it starts going past 3 kHz, it's going to get edgy in the top end. I don't want that, so I've done it in parallel. It's sending out 7 and 8 into this channel here, where I've got Kelvin Tone Shaper, and at the end of Kelvin Tone Shaper in post, I'm using a low pass filter with a 12 decibel per octave attenuation from 1 kHz. And in Plugin Doctor, you can see what the frequency, the linear analysis of that parallel chain is. It's just adding these harmonics to this center range. However, the problem with this is it's also adding the harmonics and the fundamentals back into the signal. I didn't want that. Now, I know in Kelvin Tone Shaper you can shape where the harmonics are and whatnot, but I wanted to have a little bit more push and play with this. What I've done is I've used Kelvin Tone Shaper again here, but without any harmonics, so just on clean, and then I've flipped the phase of it. So that way, the resulting signal from the phase rotated version and the saturator is only the saturated frequencies. Now, this is an overkill. I've just went over the top because that's what I wanted to do. I just wanted to go over the top and really over engineer this. You could simply just add Kelvin Tone Shaper to your main after channel, dial this in, use the tone shaping function, and use the dry wet signal. But in my head, I just wanted to have full understanding of how the signal flow is. So the signal comes out of bus in 7 and 8, it goes parallel into a phase rotated signal with Kelvin Tone Shaper placing no extra harmonics, and then that's also filtered as well. And then that goes into a saturator with the harmonics filtered, so none of the top end comes in, and that's how I built it. So basically, it's saturation, filtered, blended in parallel, and if you want to get super nasty with it, you can rotate the phase so you're not adding any of the fundamentals in, or you could just use what Kelvin Tone Shaper is built for. It's actually built for this, where you can just shape and input how much of the low frequencies are saturating the signal and attenuate all the top and low ones pre-saturation. Now, let's have another listen, because this is just so much fun to listen to. I actually really enjoyed doing this, so let's have a listen. So anyway, if you enjoyed that, this was a lot of fun. Hit the like button, subscribe, share this with your friends, and like I said at the start of this video, if I've got some stuff wrong, let me know. Let me know in the comment section below. I want to learn too. I don't know a lot about acoustics and and physics of actual speakers, so if I've got things wrong, help me understand it better. But this was fun for what it was worth. And until next time, take care.